Okay, so welcome back to this course on logic. And can everybody hear me? Would you say yes? Okay, thank you very much. So we will continue, we'll finish off our discussions on Scolamization and Scholam form. Okay, so we are almost at the end of our discussion on this topic. And but if I give you a quick reminder about where we are, so maybe I just, so I think it's a quick reminder. So we started with, and we became interested in looking at so-called normal form formula because it's much simpler. I mean, first order logic, if we want to design an algorithm or want to do some meta theory to prove some properties about first order logic, one of the biggest hurdle is that the formulas are so complicated. So if we can somehow manage to so-called change the formula in such a way that it is okay to focus on the transformed formulas only, so then that may simplify many things dramatically. So one of the things that appears quite often is we studied something called the Prenux form. Especially something called the rectified Prenux form. So this is the formula where all the universal and existential quantifications are taken out. So the typical formula looks like this. Exists X for Y, maybe for Z, and exists W for A. We have some formula F. Okay? And then inside the formula F, in formula F, it doesn't contain any quantifications. This is called quantifier free formula. And we said converting any formula, maybe G, can be transformed into this rectified Prenux form quite easily in polynomial time. So, and then the idea is first push all the negations to the base case using De Morgan's law, and then rename all those quantified universal and the universally quantified and existentially quantified variable, so that we end up with a rectified formula, and then move quantification outside using one of the those equivalence relationships that we studied before. And I think if you just don't worry too much and just do what your intuition tells you, then you can easily transform G into this rectified Prenux formula without so much trouble. But now the more interesting bit is that once we have this rectified Prenux form, and by the way, these two formulas are equivalent. Okay? So they mean the same thing. But once we have a rectified Prenux form, and we can convert it to Scolam form. And this is a much more dramatic transformation. Transformation itself is quite simple, but the formula that we end up with much simpler. So in this formula, in the case, all the formula only have a universal quantification outside, and then we have some formula F prime. Okay, maybe have A here, and this formula, so this is a much simpler formula than with this Prenux form. That's because it doesn't have any alternating universal and existential quantification. I mean, if you are familiar with complexity theory, then this alternation of universal and existential quantification, in a sense, makes problem harder. Okay, makes formula more complicated from computational complexity perspective. And in many sense, that makes formula much more complicated. But Scolam form, it's quite simple. We only have a universal quantification. And Scolamization is a process that transforms in the formula in rectified Prenux form into the Scolam form. So this is called Scolamization. And then this Scolamization is a bit different from the transformation to the Prenux, rectified Prenux form in the sense that it only preserves satisfiability. Okay, so it means it's a equi-satisfiable transformation. I mean, I think this is maybe the right terminology. Satisfiability preserving and reflecting transformation. So which means that this transformation, if we do this, original formula is satisfiable precisely when the new formula is satisfiable. Their meanings are related, but they are not equivalent. Okay. So then the question becomes, how can we do this Scolamization, which actually dramatically simplify the formula, and then it will become the basis of theorem proving for first order logic. And the idea is to introduce constant symbols to, and then the function, new constant symbol and new function symbols. So for instance, so that's really, I mean, it's based on this proposition, which is called Scolamization's theorem, proposition called Scolamizations. What it says is that if we have a formula F, which have a bunch of universal quantification followed by existential quantification, and some formula G may have other universal or existential quantification itself, and the formula is rectified. And in that case, if we pick new function symbol F, whose error t is n, so F doesn't appear anywhere inside F, this capital, the small f doesn't appear anywhere inside this capital F. And then if we replace this existentially quantified z by function small f applied to y1 up to yn inside the G, so then this formula F and the new formula F prime are equi-satisfiable. F is satisfiable if and only if this F prime is satisfiable. Okay, so we're gonna prove this theorem, but now let's answer this question number 3, that this exercise 3. And this proposition allows us to do this Scolamization. And how can we do it? So actually the base case, I mean, which is not quite mentioned about this Scolamization proposition, is that if we only have an existential quantification like the one here, so in this case, we have existential quantification, there are no universal quantification beforehand. So then we have something very similar to this Scolamization, where instead of a function symbol small f, we can just use a fresh constant c. Okay, so but we assuming this simpler version of proposition is true, okay, which is actually true, and we can convert the formula that you see here, I mean this guy, and we can Scolamize it by repeatedly applying this proposition. So first, we pick some fresh constants, fresh constant c. By fresh, I mean the constant c doesn't appear anywhere inside the formula. And then we replace this formula by like this. For c exists w, for a, and where f, where we replace x by c. Okay, so that's step number 1. And then because of the proposition, if the original formula is satisfiable, the transformed formula is going to be satisfiable. And then now to make it into a Scolam form, we have to get rid of another existential quantification, this time this guy. To do so, we know that there are 2 free variables that appears here, which is y and z. Okay, so we introduce new function symbols. Arrow T2, function symbol f, small f. And then we apply essentially the proposition. So then the proposition said, if we write it something like this, I mean, the actually, right. So I think actually I just applied this proposition in a simpler form. The proposition say, I mean, this and then the original one is equisatisfiable, but C is fresh and this is rectified. This substitution is the same as for Y, Z is W, A, where in F we replace X by C. Okay. And the same thing here for all Fn. For this formula, we replace W by F applied to Y and Z. But then because, I mean, it's rectified and then the F is fresh, this one, by the definition of substitutions, but we have formula like this here. F where W is replaced by small y and z. Okay, so the proposition tells us how we can convert the original formula into a score-length formula while preserving and reflecting satisfiability. So proposition ensures the things that we obtain by introducing fresh constancy is equisatisfiable with the original one formula. After this change by new function symbol f, we again have an equisatisfiable formula. So that all, I mean, the proposition is a key to do the Scolamization. And now the question becomes why this is true. So, and then it turns out proving this is actually quite easy. So, well, we have to show that, I mean, we have to show equisatisfiability. So we first prove this direction, which is if the original f is satisfiable, we say f prime is satisfiable. So suppose f is satisfiable, that means that there is a structure such that this is true for some A structure. Okay. So now we have to find, so what should we do? So what we have to do is we have to find some structure A prime such that A prime satisfies this new formula F prime. So that's what we have to do. That's what equisatisfiability means. And now the question is, how should we find A prime? And then for A prime, it's I mean, A prime and A are in some sense over different signature. A is of a signature which usually without containing this newly introduced function symbol F. So A doesn't say anything about F. Small f. And then this newly introduced A prime should say something reasonable about F. So if you do this correctly, then we will end up with A prime that will satisfy the new formula F prime. So instead of going all the details, I will just give you how we can define F, and then the rest, if you just follow the semantics, then you can easily prove A prime should satisfy F prime. So the question becomes, how should we define this meaning of this small f under A prime? So that's, I think we wrote it like this, perhaps, or subscript, I forgot exactly. So we have to say, okay, how this symbol small f will be interpreted under A prime. This will be, maybe it's a subscript. So let's use that instead of A prime, let's use B, right? Because Okay, so this one should be a mapping from U, B. Now we have a n parameter and U, B. And now when we define B, okay, so we define B just like A, but we change, well, we add the interpretation of F by mapping it to FB, which we will define. Okay. So now the question is, how should they do this FB prime? So this one, because it's the same as A, underlying universe is the same as A, this is the A, and this is underlying universe of A. Okay, now how should we do it? And it's quite simple. So we said FB, which take n elements in the underlying universe, small u1 up to un. It's gonna be chosen to become u. And then now we have to describe how this u is chosen. This u is something that makes the following true. That makes y1 and z f to be true. Okay, so we know fa set, not f here. I use g. We know that so A satisfies F, and then F is a formula which have we order universal quantification followed by existential quantification. So if we plug in the U1 for Y1, U2 for Y2, UN for YN, then there should exist some value, some binding for Z, which will make the G true. Okay, so if we plug in U1 up to UN, there should exist some small u in the underlying universe of the structure of A, such that, I mean, this entire updated version of the structure should satisfy the formula G. So we just use this, say that this u, which exists because of the satisfiability of the original formula, we say that's going to be the result of applying this function f to u1 up to un. And this is always possible. So we have to make some choice here, but this is always possible. And whatever choice we make, that's going to be the right choice in the sense that our new structure B is going to satisfy this f prime. If you think about it, that's in some sense obvious. That's because now we are interpreting this f prime. We are checking whether f prime holds under B. But then whenever we have this universal quantifications, okay, whenever we have a binding for this universal quantification under B, we will, when we apply this function f to this binding for y1 up to yn, we will end up with the right value because, I mean, the value will be chosen which in such a way that will make G true, so that we will always end up with the right value. And you can formally prove this using translation lemma and the relevance lemma and so on. Okay, so that's the way to show that, I mean, if f is satisfiable, then f prime is satisfiable. And the other direction is also quite easy. I mean, it's even easier. So if we have so suppose for the other direction, we have some structure B, which satisfies f prime for some B. Then we have to say, we have to come up with, so what we need to do is to find some structure A such that A satisfies F. Now for this structure, all we need to do is just to say A is essentially the same as B, where we forget, may I write some notation like this? We forget about what B says about this function symbol F. So here I'm assuming A is of a signature which doesn't contain this function symbol F. And so B is over the signature, which contains this function symbol small f. So we just get rid of this extra binding so that we get an appropriate structure. If you do it, this A is going to satisfy F. Why is that? That's because now to see this, and to show this is really the case, we have to say it for all A1 to maybe I use the U1 up to UN in the underlying universe of A, which is same as underlying universe of B. We should, so there should exist U in UA such that A where Y1, U1, YN, UN, Z, U. This guy satisfies the formula G. Okay. But so now we have to make this choice. We have to choose that there should exist U. But for this choice, we can set U to be applying this functions symbol under, applying these functions meaning of this function under B to U1 and UN. Okay. So if you do this, then here's what we have. Okay. So if you do this, then we can show that this A actually satisfies the G. Why? The reason is that, so if we do this, then this one is say the same thing as, because A and B are essentially the same. So I will write it like this. So we get rid of this, the F part, and have I feel like I'm saying something obvious, but let me just continue and finish this. UN, and then G is bound to U1 up to UN. And so this is what we have to prove. This is what we have to show. But if we now use translation lemma, so this is equivalent to the first. There is some general version of the relevance lemma where, because function symbol f doesn't really appear, this satisfiability is essentially identical to this one. And then now we are using translation lemma. Okay, because we can use translation lemma because this one is same as B apply to B. So it's a B Y1 U1 YN UN. Under this structure, we interpret this function application 1 YN. So this is really the interpretation of this term, which is apply F to Y1 up to YN under this structure. But now by the translation lemma, which say how substitution on a formula is related to substitution on the structure. This is say the same thing as B. This looks like A. B. UN satisfies G, where F of Y1 to YN is replacing z inside the formula. Okay, but I mean, but that's something that we already know. I mean, this is exactly, or this is true for all y1 and yn, and that's, so say for u1 up to un, there's also for u1 to un. Here again, we have a for u1 to un. And but this is say the same thing as b satisfies for y1 yn replaced by z. And that's exactly the formula f prime. So we start with b, which satisfies formula f prime. So we started with b, which satisfies formula f prime. And from there, we defined a, and then we show that this a satisfies the original formula f. It's a bit complicated, but the basic idea is really simple. The whole idea is just, I mean, this step is the whole idea. So using f to find the appropriate witness there. So once you do it, then you can prove the theorem quite easily. Okay, so that's the Scolamization. And now we can use, as I said before, we can put all the things together and said every formula in first order logic can be converted into equisatisfiable formula in Scolam form in polynomial time. And then the step, it just combine all the steps that we learned so far. We first convert formula of first order logic into rectified Prenux form, which preserve the meanings. In other words, it's an equivalent formula. But then we apply this Scolamization systematically to get rid of all the existential quantification in the Prenux formula. That process will only preserve satisfiability and preserve and reflect satisfiability. So we end up with an equisatisfiable formula. So now this is, although I stated as a theorem, really it is a theorem, the key proof, and then there's some important aspect of the theorem is an algorithm. So apply the algorithm kind of implicitly stated by this theorem to these three examples and convert these three examples into equisatisfiable Scolam form. Okay, so I will give you about 5 minutes to do so. Okay, let me solve this. I will only solve the second question here. So we just be okay. Okay, so here's the number 4. So it's quite simple. So first we move negations from outside to the inside. So then we end up and also replace this implication by disjunction and negation. So then we have for x is to y p x y z disjunction, and then not disjunction. So here's we have a conjunction. Then negation. We have a universally quantified x. And then if I put one more negation and cancel, then put the disjunction here, we have y, q of yz, and disjunction of r of x. Now, if you move negation to the inside, and this is what we did before, but this is perhaps one of the most complicated formula. So I want to do this again. So we have exist x, and then negation goes in, and then change this disjunction to conjunction and put a negation here. One negation goes out, but if we go in, that change the existential quantification. So we have q, y, z, and negation of rx. Okay. So now we want to rectify this. To rectify this formula, we rename variables. So we rename this x, the existentially quantified x, to x prime. So x became x prime. This also became x prime. We rename y to y prime. So we renamed it to y prime, and that's it. And now we move all the quantification out. So if we move this entire thing inside of, so we can first take this universal quantification out. So then this part of the formula becomes exists x prime for y prime, q of y prime z, and negation of r of x prime. And then now we move this formula inside this universal and existential quantification, and then take quantification out. So if you do this, then we will end up with for x exists y exists x prime for y prime, p of x y z, and negation of q y prime z, and negation of r x prime. Okay, now we have to do Scolamization. So far we preserve the meaning, but now from now on we only preserve the satisfiability. So we do Scolamization. So we first Scolamize this existentially quantified y. Before y, there's only one universal quantification, which is x. So we introduce a small f, and then replace all y by f of x. So that's what we're gonna do for the first existential quantification. If we do this, then we end up with this formula p of y gets replaced by f of x. So we have f of x, z, and q y prime z, and negation of rx prime. Now there's another things that we have to get rid of. So for this x prime, again, there's only one universal quantification before. So now we introduce a new fresh function symbol g in this time, and then we replace x prime by g of x. So if we do so, then we end up with a formula, say for x, for y prime. We have p, x, f of x, and z, and negation of q, y prime, and z. But the last part, x prime, is going to be replaced by g of x. So we end up with a new formula where all the existential quantifications are gone, universal quantification is out. So this is exactly Scolam form. And because of the theorem that we used, or the proposition that we used in the previous slide, this new formula that we get is equisatisfiable to the original formula that we started with. Okay, so that's a Scolamization. So if you think, that's true. So I think that what Juyeon is saying is when we convert a formula into a Prenux form, sometimes the order doesn't really matter. For instance, for this particular example that we have, for exists x prime for y prime, we could have moved, say, this part inside of this quantification. Okay, so then the order will change. So we have exist x prime first, for y prime next, for x, and then exist y, and so on. Okay, so what does that mean? That means during this convergence, we may end up with the multiple, there are multiple possible the Scolam formula that we may end up with, depending on the particular strategy of doing this Prenux form conversion. Okay. All these converted Prenux formula are equivalent, but the shape of the formula is different. And then the shape has a great influence on what kind of a Scolam formula we get. So if you ask the question, now suppose you became a person who are interested in building automated theorem prover, and the pre-processing step of the automated theorem prover is doing this Scolamization. So then your observation just indicates the performance of this your theorem prover may depending on what kind of pre-process, what's going to happen in this pre-processing step, which convert any first order logic formula into a Scolam formula. Okay. Maybe some conversion works much better for the theorem prover. Some conversion works much worse. Okay, so that picking the right decision is not entirely obvious, but that's one of the interesting questions one can work on. So you are exactly right. When we the Scolamizations, then we may end up with Scolamization is not a deterministic step. It's a very non-deterministic step with multiple possible target with the different consequences on the performance of this. What's going to follow up the kind of main algorithm that you want to run later. But that's so your observation is right. And other reason is why that happens. That happens because Scolamization is really assuming some dependency among existential and universal quantification. During the conversion, we have a specific knowledge about which depends on what. So if you have existential quantification, Scolamization say it potentially depending on all the universally quantified variable before. But these pre-next form transformations say actually we know more. We know that sometimes existential quantification doesn't depending on what's going to happen by the universal before. But all that information disappears when you convert formula into the Prenux form. Okay. Okay, so do you have any other questions? Okay, good. So then we move on to the next step, the next topic. So next topic is a Herbaline Theorem, and here we're gonna really talk about some semi-algorithm for checking unsatisfiability of a first-order logic. So this is a semi-algorithm. So actually, I think later we will show that checking satisfiability or both of them are either undecidable or more than undecidable. So it's not possible to come up with an algorithm, but here's a semi-algorithm, and which also form the basis of many first-order logic theorem proofs. Okay, and one can say that this Herbaline theorem we're going to talk about is actually what, and then also this ground resolution is really the core part of the course. So it will bring many things we discussed together. It will bring compactness theorem and the Scolamization, and also some extra bit, which is a Herbaline theorem. So it's a quick reminder of where we are. We just discussed about if we have a formula, any formula can be transformed into the Prenux form first, rectified Prenux form, and then we can also transform it into the Scolam form, preserving and reflecting satisfiability. Okay. And then, so we're gonna, what does that mean? That means that now if we are interested in the satisfiability or unsatisfiability, it doesn't matter. Actually, we are usually interested in the unsatisfiability of the original formula. So suppose I have a formula G, erasure, it's not clicked. So if we, suppose we are interested in unsatisfiability of the formula G. So this is just some first order logic formula. And typically this unsatisfiability question makes sense because we are trying to prove by contradiction. So if you want to prove some implications, you put a negation of the conclusion, want to prove by contradiction. So typically we are interested in answering this unsatisfiability. So then what we discussed so far say that actually if you are interested in unsatisfiability, we can actually simplify the problem a little bit by doing this Scolamization. So if you Scolamize, so G get G prime by Scolamization. And then one thing we learn is that this G and G prime are equi-satisfiable, which means they are also equi-unsatisfiable. So if G is unsatisfiable, if and only if G prime is unsatisfiable. What does that mean is answering G is unsatisfiable is exactly the same thing as answering G prime is unsatisfiable. So G prime is much simpler than G in the sense that this G prime always looks like for x1 and for xn and some G prime star, which doesn't involve any quantification at all. So it's a much simpler formula. And this is what we learned so far tells us to do, gives us. And then now still checking unsatisfiability of this formula is not entirely obvious. Okay? That's because, if you think about what unsatisfiability means, it means that whatever structure you pick up, this formula is not quite true. Also, yeah, so that's quite a bit of work if you want to really want to check all those structures. There are really, really many structures that you have to check. So some theorem we're gonna talk about, which is called Herbaline Theorem, will tell us first, instead of checking, so we have checked this is unsatisfiable, we have to really consider lots of, these are the all structures. We have to check all the structures and see this formula is not satisfied by any of the structure. But Herbaline theorem will tell us actually to check the unsatisfiability of this formula is sufficient to check only some of them. So if you only check unsatisfiability for some subset, which is in some sense very syntactic, and that checking this formula is unsatisfiable with respect to this subset is enough to show this is unsatisfiable. So we are not checking everything. That's what we have to do according to the definition of unsatisfiability. But Herbaline theorem allows us to save some energy. So we can just focus on this subset. Checking unsatisfiability of this subset implies unsatisfiability for the entire set. So that's going from here to here is what Herbaline theorem allows us to do. And then for once you have this Herbaline theorem, then we're gonna use compactness theorem to actually derive a semi-algorithm from there, which is gonna based on resolution theorem proving. Okay, so that's the big picture, and then let's move on. So then the one key concept in the behind the Herbaline theorem is something very obvious. It's something called the ground term. Okay. So as I said before, in first order logic, we have two kind of syntactic entities. One is called terms, the other is called formulas. Okay. Ground term is a specific kind of a term which doesn't contain any free variable at all. So for instance, if we have a signature which contains two constants C and D, functions, unary function symbol F, binary function symbol G, predicate symbol F, P, and Q. The ground terms are like a C, D, something that you can construct, all the terms that you can construct without using any variable according to this signature. So it can be C and D, F of C, F of D, and so on. So there are infinitely many. So if as soon as you have a function symbol, there are infinitely many ground terms. They are always countable, but there are infinitely many ground terms. So here to some, I will give you 1 minute to think about this exercise. Think about what would be the signature whose ground term is isomorphic to the set of integers. So by set of integers, I mean set of natural numbers. By set of natural numbers, I take computer scientist or maybe category theorist perspective where natural number is starting from 0. So mathematician often say natural numbers are starting from 1. Computer scientists usually say start from 0. Okay. I'll give you 1 minute to think about this as an exercise. Okay, so the answer is really simple. The simplest signature that you can think about is a signature which contains some constant symbol called 0. And then arrow T1 of function symbol called successor. Okay, so this is arrow T1 function symbol. So if, in this case, if I generate all the ground terms is going to be 0, successor applied to 0, successor applied to this term, which is S0, and so on. And then this guy can be mapped to natural number 0. This guy can be mapped to natural number 1, natural number 2. So it's an isomorphic to the natural number. In fact, I mean, this set of ground term is called initial algebra of this signature, and that's essentially a way to define set of natural numbers in a more kind of, in a categoric way or more in a bit some way. Okay. So anyhow, this is a ground term looks like this, and that's isomorphic to the set of natural numbers. Church numerals are a bit different. I mean, church numerals are usually defined in terms of applying the function applications. So a bit similar, you're right. But this is church numeral has more meaning, which is if number n really means we are applying the same function n times. Here, these terms do not have any meaning at all. Yeah, so Jongik's question, yes, the signature doesn't have to have any predicate symbol at all. It doesn't have to have even constants. Doesn't have to have the sometimes a function symbol. Okay, good. So if you have any other questions, I mean, just ask them in the chat box, or if you require more time, you can ask me at the end. So that's different because if you arrow T1 function symbol, so arrow T1 function symbol, I mean, they are different. It's a one functions and the other is the predicates. Okay, I see where you are, where you come from. So arrow T1 function symbol, It's really, if you think about its interpretation in the structure B, that's going to be a mapping from U of A to U of A, underlying set to underlying set. Error T1 predicate symbol, B is going to be a subset of U of B. Okay, so they are different, but you can view these two things are a bit related by saying, okay, actually the subset can be understood as a sometimes called indicator function, sometimes called characteristic function. So this one can be understood as some mapping. Maybe I just call it G of, maybe I did this notation. I write this notation as a P of B. So it's U of B to 0 and 1, such that, this guy returns 0 if the input element doesn't belong to this set, returns 1 if input element belongs 1. So in this sense, it's a bit related, so you can kind of relate them together, but they are not exactly the same. One is talking about subset, the other is talking about function. And then, okay, what I'm saying now is also, if we make you confused, don't have to worry about it at all. Okay, the functions more generally can be understood as specific kind of relations on UB cross UB. Okay, so how does it build as a relations? It can be understood as you just put all the elements of U, it will be U together for all UB. So function induces a binary relation. This type of unary function, binary relation. But it's a specific kind of a binary relation. So some model theorists say functions are specific kind of relations. So, and then predicates are really representing relations. So they forget about the function symbol. They also do not include the constant. They only focus on the predicate symbols. But as I said, if what I'm just telling you make you confused, you don't have to worry about it at all, okay? Okay, so maybe clear all. Right, so then now here's a key, one important concept, which is called Herbaline structure. So this is a specific kind of structure, okay? So we are given signature sigma, we assume that signature contains at least one constant symbol. That's because we want to make sure the structure that we are talking about contains at least one element in the underlying universe, its universe. So we have a signature which contains at least one constant symbol. And certain structure over sigma is called Herbaline structure if we satisfy the following property. Okay, the first condition is saying the underlying universe U under the signature, it's a set of ground terms over sigma. Okay, so in a sense, the universe is fixed. It has to be the set of ground terms over sigma. This set of ground terms is exactly what you saw in the previous slide. So this means U of H is fixed. Okay. So there are no flexibility. Every Herbaline structure should have exactly over the same sigma, should have exactly the same the underlying universe. And now, because the underlying universe is fixed, we can start to talk about how this structure should interpret constant symbol and function symbol. And then you say the constant symbol, its interpretation is itself. This may be a bit confusing to some of you, but now imagine, suppose if our signature sigma consists of constant C and say unary function symbol F. So then this U of H is going to be C, F of C, F of C, so on. So it's an infinite set. Now what this second clause telling us is now interpretation of meaning of C under this universe should be C gets mapped to the element C in this set of ground term. Okay. And then for function symbols, its interpretation, so this F in here, F sub H, that has to be a mapping from U of H mean, in this case, n to u of h. Okay, so you say that if it takes the n ground term, it will produce a new ground term. Okay, so actually, I mean, you don't. I mean, this one you can just write it like t1 up to tn. So if you take an n ground term, which is a parameter of this function, so we're gonna produce a new ground term. So with n ground term, we're gonna produce a new ground term. And the way we construct a new ground term is by just putting f in front of this, I mean, as a function symbols, and we construct for this application ground term. So if I write this ground term as a tree, so say, sometimes people represent it as a tree, saying we have a constant function applied to C, function applied twice to C, and so on. So then for this interpretation, say if I given n trees which represent ground terms, then we're gonna return a new tree which have f as a new root and has a t1, t2 up to tn as the subtrees. Okay, so I mean, this is sometimes very obvious, but I'm telling you because I mean sometimes it is very confusing because I mean we are talking about interpretation at the same time you're using the same symbol. But the point here is that underlying universe is constructed very syntactically. It's constructed using ground terms, and then we are using these ground terms to interpret constant symbol as constant term in this underlying universe, u sub h, and each function symbol is interpreted as just term construction by putting this function symbol f. Okay, so now there are a few things that we can prove in this case quite easily. So let me just show all the things. So try to solve these two exercises. The first exercise is that for any, okay, now before going this, now for this Herbaline structure, many things are fixed. Underlying universe is fixed. Interpretation of a constant symbol is fixed. Interpretation of function symbol is fixed. But important bit is that interpretation of predicate symbol is not fixed. Okay, so there is one flexibility, which is you can choose different interpretation for the predicate symbols. So choosing one interpretation, you get a one Herbaline structure. Different one, you get a different Herbaline structure. So there are not if you have a predicate symbol in the signature, there are usually infinitely many Herbaline structures. Okay, so now that here's a proposition I want you to prove for any Herbaline structure H, ground term T. If you interpret this term T under this Herbaline structure, it will become essentially itself. Okay, I mean this term T itself lives in the underlying universe, and that's going to be the interpretation. So that's the proposition. I want you to prove this using structural induction. And second, we have a translation lemma. The original translation lemma was a bit more complex. So this original translation lemma was written like this. If you have the H satisfies F, T is replacing X, where T satisfies some conditions on bound variable. If and only if H, actually this is, you can easily see the proof, but H of T. So that was the original translation lemma, and then there was some conditions on T. So that's the usual translation lemma. And then what this theorem tells us is that for Herbaline structure, actually this translation lemma can be simple because we don't have to worry about this. Also, we say this one can become equal to T. So these are the two things that you need to prove. So I will give you maybe 2 minutes to prove the both proposition and the translation lemma. Okay, so let me show the proof. Okay, let's change to a mouse. Okay, and right. So the proposition is by induction. And the structure of T. Okay, because T is a ground term, there are only two cases to consider. The first case number one is that this T is equal to constant. In that case, if we have interpretations of C, by definition is exactly the same as C. I mean, that has to be C of sub H, that is exactly C. Yeah, by the definition of Herbaline structure. Okay, and then the second, actually we do all of the case. I mean, this case is a variable. I mean, this case is true vacuously. That's because, I mean, we said T has to be a ground term, X is a variable, so it can't really satisfy these conditions that implicitly imposed in the proposition. The third case, if T is a function applications, Tn, so then, I mean, we also know that T1, if T is a ground term, T1 up to Tn are ground term. That's because, I mean, T doesn't contain free variables. T1 up to Tn shouldn't contain free variable either. And so we can use the induction hypothesis. So by induction hypothesis, so we know that for h of Ti is equal to Ti for I. And then we now interpret h of T, which is h of f T1 up to Tn. And by the definitions of the semantics, and this is same as use the meaning of f under h, and then interprets each of these T1 up to Tn. And interpretation of T1 up to Tn by induction hypothesis, that's the same as T1 up to Tn. And this is really what we proved. And now we look at by the definition of Herbaline structure, that is same as T of f by Tn, same as T. And this is definition of Herbaline structure. So this is quite simple induction. And now for the second translation lemma, we can actually just use the translation lemma in the most general translation lemma. Okay, so because T is a ground term, it doesn't have any, so T doesn't contain any free variable. I mean, it doesn't contain any variable at all. So we can apply the translation lemma of the original translation lemma. What we have is H satisfies f T of x if and only if H x gets mapped to H of T satisfies f. But by the lemma that we showed, this is equivalent to hxt satisfies f. This is by proposition just shown Okay, so it's just said for ground term and Herbaline structure, the translation lemma had some simple form. And both are not very surprising result, but it's quite convenient tools that we can use. Okay, so now I'll move to the next. And then we're gonna look at the results. Yeah, we have a very few minutes. So let me just give you some story about Herbaline and then statement of the Herbaline theorem. And then we will prove the Herbaline theorem and then study its consequences. So Herbaline is according to what I read in Wikipedia, Herbaline is, he died very young. So he died 23 when he was 23 years old. I heard he finished his PhD thesis when he was 21. And then although he was very young, like a kind of famous mathematicians like Hasse and Courant, they thought Herbaline is one of the best young mathematician during that time. And I heard that he works on the two kind of areas in mathematics. One is about proof theory, which is related to what we're going to talk about, and proof theory and foundation of mathematics. So that's one area he worked on. So he came up with Herbaline theorem that we're going to talk about. Also, he came up with the notion of recursive functions. And one big result in that area he came up with is the consistency of very weak system of arithmetic. So that was the big question at the time. So Hilbert posed the question of proving consistency of the logical system consistency of the logical system for arithmetic or number theory. And so that was, I think, that's one of the big questions he posed. And in a sense, Herbaline answered that question for a bit weak version of the number theory. And that doesn't contradict what Gödel proved, because his system, the Herbaline system, was weak. But he also did some work on the algebraic number theory. So I heard he had some theorem which is named after him in algebraic number theory, as well as some construction in homology has a name, his name there. And so he's quite famous and very smart. But what happened was that when he was 23 years old, he went for a hike in Alps with his friend, and then maybe he fell in some cliff, and he died at the time. So so that's the story. And maybe one more of the story is just be careful if you climb mountain. Okay. So the Herbaline theorem that we're gonna study is the theorem of this form. So it says the following: if I have a formula f, which is in Scolam form, so you have a universal quantification and f star, which is a quantified free formula. So then this theorem said that formula f is satisfiable if and only if it has an Herbaline model. Okay, and as I said, to see satisfiability of f means that for all structures, so there are lots of structures which we can choose, and then it said that there are some structure that satisfy this formula, but there are lots of structure there. But among these structures, Herbaline's model or Herbaline structures are subset. Okay, it's a specific kind of structure. So it's some very small subset is Herbaline structure. So what this theorem says is that if formula f is satisfiable, so then there always, so if formula f is satisfied by some a here, so you can always find some Herbaline structure a prime such that also satisfies the formula f. Of course, the other direction is quite easy. If some Herbaline structure satisfy the formula, then obviously there is a structure which satisfies the formula. That's because Herbaline structure is also a structure. So the direction of this f has a Herbaline model implies f is satisfiable. That's an easy direction. And it's also not very useful direction. But important direction is the other direction, which say that if f is satisfiable, which means that there is some structure which satisfies f, then there always exists very specific kind of structure which also satisfies f. And that specific structure is called Herbaline structure. And as I said before, In Herbaline structure, many things are fixed. So in every Herbaline structure, this underlying universe is fixed. It's a set of ground terms. Interpretation of constant, interpretation of function symbol, they are all fixed. The only flexibility is interpretation of predicate symbol. So this is the only flexible part. But the theorem say, if we exploit, kind of make the right decision for this flexible part, we can make formula F true when formula F is satisfied. Okay, so yeah, that's it for today, and we're gonna prove this theorem and then study some consequences of this theorem, especially about first order theorem proving. Okay, so that's it for today. I'm gonna stay here for 5 more minutes. If you have any question, you can stay and ask me.